Okay, so in the previous chapters, we talked about static electricity. Electricity is stored on things like capacitors, where you had a fixed amount of charge and a voltage. So now it's time to see electricity in action, to see electricity in motion, and that is current electricity. So let's start by looking at an analogy between water flow and electrical charge flow. So here you have one tank, and here's a second tank, tank 1 and tank 2. These are filled with waters to different levels. As you can see, it's taller over here, and it's not quite as tall on the other side. So if you connect the two by a tube, water is going to flow from the left to the right. So the question is, what governs the rate of flow of the water? What causes the water to flow faster or slower? So here are some of the parameters. So this tube, it has a length L. So this thing over here, by the way, this is an L. Okay, it's a lowercase l. It has a length L. It has a cross-sectional area A. So that governs how much space you have for the water, for the liquid to flow. Then, depending on what kind of liquid you have, whether it's water, alcohol, or something like pancake syrup, you have different viscosity. You have different thicknesses, stickiness of the liquid. So the viscosity is a factor in governing how quickly the stuff will flow across. So first of all, here's a thinker question for you. Let me move this up a bit. So what will the flow rate depend on? The flow rate is basically how much of the stuff flows across. So it could officially be measured in meters per gallon, cubic meters per time. How much of it flows across. You might measure it in gallons per minute and things like that. That's the official unit, cubic meters per second. So what controls the flow rate? How does it depend on the length, how long the tube is, the viscosity, how thick or thin the liquid is in terms of flowing, and the area of cross-section, and finally the height difference. So if you have a tiny height difference versus a bigger height difference over here, how does it affect the rate of flow? So think about it for a few seconds, write down your thought, and the answer is coming up shortly. So here's the answer. The flow rate, how many cubic meters per second flow across every second, that's proportional to the height difference. If the two tanks are at the same level, water will not flow to the left or the right. It'll be a symmetric situation. So the bigger the difference in height, the bigger the difference in pressure, the faster the water or other liquid gushes across to the other side. Number two, the area. If you have a skinny pipe versus one with a bigger cross section, it's like having more lanes of traffic. It's going to flow faster. Number three, the length. If you have a short tube versus a long tube, with a longer tube, the liquid has to struggle more to get across to the other side. So it's inversely proportional to the length. That's why L is in the denominator. And finally, the viscosity is going to depend on what kind of liquid you have. Something that's thick, like maple syrup, honey, and so on, sticky stuff, is going to flow at a different rate than something that's kind of thin, low viscosity, like water, ether, alcohol, and so on. So these are the four things which govern the rate of flow of a liquid going from, which is being driven by a difference in pressure caused by a difference in height for these two tanks. So the same logic carries over to electrical charge flow. So let's see how that happens. So instead of the difference in pressure, the difference in height that you had between the two tanks, here you have two spheres charged differently. So you have two identical spheres, same in size and all that. More positive charges are stuffed on one side compared to the other. So these are under greater pressure, greater electrical potential. So that's going to drive the positives to basically to flow in this direction. And this rate of flow in the context of electrical charge flowing, it's referred to as the current, is symbolized by the letter I. So you have an I flowing across. And the rate at which the charge is flowing, the electrical current, it depends on similar factors to what you had for fluid flow. Here, once again, the more the delta V, that's like having bigger height difference, bigger pressure difference for those water tank, more delta V between these two. So this is a V2 and this is a V1, and V2 is more than V1. So that's going to drive the flow faster. And number two, the area of cross section. So if you have a skinny wire like this versus a thick wire like this, you have more cross section, more it's like more lanes of traffic supported by that wire. The charge is going to flow faster. So the current is proportional to the area of cross section. Number three is inversely proportional to the length. So just as you had for the fluid flow, if you have a short wire versus a longer wire, more struggle, more difficulty in getting across. So it's inversely proportional to L. And just like you had this eta, coefficient of viscosity, honey versus water, for example, similarly, it's going to depend on what is this material through which the current is flowing. So we talked about insulators and conductors previously. Same thing, even if you have two different conductors like copper, aluminum, silver, and so on, they all have different conductivity, like the difference between pancake syrup, honey, water, and so on. So you have something in the denominator, which is the resistivity. It's kind of like the viscosity in the context of charge flow. So these are the four things that govern electrical flow and the rate of flow of charge. And that's symbolized by I, which is a symbol for the electrical current. So far we've been talking about the difference in potential, the difference in height, the difference in pressure driving the stuff. But in current electricity, you only ever have a difference. There is no such thing as an absolute potential. So when we talked about the Van de Graaff generator previously, you had the big dome that gets charged to like 1,000,000 volt. When you touch it, that is a potential. You're referencing it to the earth, to ground. But when you're talking about circuits and current electricity, it's always a difference. So for example, when you're measuring a potential difference, voltage, you'll use something like this. Two wires come out of it. For this to work, you always touch the circuit at two different places. So what you're measuring is always a difference in potential. For this reason, we drop the delta and we just write V. So V is already a delta V, but the delta is not mentioned because you always have the delta. So let's rearrange the previous equation that we had. You had the current I equals delta V A over L times rho. Moving things around, the voltage V, once again we drop the delta, that's equal to I times rho L over A. Many a times the rho, L, and A, they are fixed. So you can lump these together into a single quantity called R. So everything in the bracket, rho, L over A, we call it R. So this gives you a connection between the voltage, the current, and this combined quantity. This R is called the resistance, and it's measured in ohms, and the symbol for that is a omega. This is a capital omega. The symbol for resistivity, by the way, it's in ohm meters, basically. So one quick piece of unfinished business. I forgot to mention the unit for electric current. So the electric current, symbolized by I, is the amount of charge that flows per time, or delta Q by delta T. So delta T is measured in coulombs, and time, of course, the standard unit is seconds. So a coulomb over second is the unit for current. But because the current is used so often, it has its own name. So this coulomb per second is an ampere, and symbolized by capital A. So that's basically the unit for electric current. Sometimes it's known by its nickname amps. You have a circuit that's drawing 5 amps basically. So that's the unit of electric current. So let's now do a quick example to see how all of this fits together. So to use this formula, basically, the one over here. There it is, okay. So you have a connection between the resistance, the resistivity, the length, and A. So we are going to calculate the resistance of a 3 meter long 18 gauge wire. So here is 18 gauge wire, if you can see this. So that's 18 gauge speaker wire, is used for connecting loudspeakers to amplifiers and things like that. So this was bought for the handsome price of $3.49. That's 18 gauge wire. So you can measure the thickness of this wire, the cross-sectional area, using one of these things. And once you have that, that gives you the gauge of the wire. So this is 18 gauge wire, and we find that the cross-sectional area of such a 18 gauge wire is 0.823 millimeters squared. Okay, and then the length is 3 meters. Then we need the resistivity. This is like the viscosity that you had in the case of liquid. So that's something that can be measured separately or looked up. This would be given to you in a problem. So the resistivity of copper is 1.7 10 to the minus 8 ohm meters. So what is the resistance? If you were to measure the resistance, that again can be measured with a meter like this. Okay, so this has a resistance setting, which is this setting over here, these white numbers. So you can connect this across that wire and verify if your answer is right. So the resistance is equal to the resistivity times the length over area from before. So 1.7 10 to the minus 8, this is the resistivity of copper. The length is 3 meters. The area of cross section is 0.823 millimeters squared. Millimeter squared is not our standard unit. Convert that to meter squared. So that's 10 to the minus 6. So putting all of this together, the resistance of that wire, a 3 meter length, about 10 feet, is a typical length for a speaker wire, a speaker cable, and that ends up being 0.062 ohms. So this is how you have a connection between resistivity, the length, the area, and the resistance. And this resistance makes a connection between the current and the voltage. And that connection between the current and the voltage, the fact that V equals I times R, this is called Ohm's law. The fact that I and V are proportional, and the constant proportionality, that's basically the resistance of the circuit. So here are some resistors. This is what resistors look like in real life. So these are different shapes and sizes. And here you have a bunch of resistors connected in parallel. You see all the ends on one side are connected together, all the ends on the other side are connected together. These are resistors in parallel. These two resistors here, these big fat ones here, they are connected in series. They may look parallel, from a geometric point of view, they kind of look like they're parallel, but it's not the geometry, it's how the current flows. So the electrical current goes through one, leaves it, then goes to the other, and then leaves that. The current sort of flows in sequence one after the other. It's like having cars in a train, basically. So this is a series connection, but here you have a parallel connection. Now, when you're drawing a circuit diagram, you do not draw pictures of these resistors. Instead, you have symbol. So in the previous chapters, we saw the symbol for a capacitor. The common capacitor is a parallel plate capacitor. So you have the parallel plate, you have these wires sticking out. Just like here, you have wires sticking out of the component. So those things, those are the wires. So similarly for a resistor, the symbol is this corrugated thing that's meant to sort of symbolize the fact that you have resistance to the electrical current flow. It has to struggle to get across. So a resistor resists the flow of electrical current. Here are some other symbols thrown in, just for completeness. We'll get into details later on. This is an inductor. So it's basically a coil of wire. Here's one big fat inductor, a very heavy thing. So as a side benefit, you can use this for resistance training, exercise basically. So that's an inductor. It slows not the current, it slows down the change in current. How that happens, so we'll see later on. Then this is a symbol for a diode. Let's look at some diodes. So these are some examples of diodes I had in hand. These are little diodes here. That's a light emitting diode. It's called an LED. And it basically glows when you connect it to a current source. This is a combination of 4 diodes inside a single package. Shortly, I'll be bringing up some pictures of these components as well. Next, let's look at batteries. So here are some examples of batteries. That's a 9-volt battery. These are both a 1.5-volt batteries, and this is a 6-volt battery here. It's what's called a lantern battery, basically. And finally, we have the switch. Here's a switch. So a switch connects and disconnects a circuit. So it's kind of like this. You have contacts inside. You can join them together. This is said to be a switch that's closed, where the circuit is closed. This allows current to flow through. When you turn something off, when you turn a lamp off, for example, what happens in the switch is the circuit is broken, so current no longer flows. So all this is happening inside this little thing over here. It might not, seem like much, but when you switch the thing, see, like this. That's basically what's happening. In there, you have some kind of contacts which are either connecting or disconnecting. So a switch that's connected is said to be closed because it closes the circuit. A switch that's open is breaking the circuit open. It's a switch that's off, basically. Okay, so that's what a switch is. So these are some common symbols that we'll be seeing as we go through this chapter. There are additional symbols. We'll deal with them when the time arises. Oh, one important symbol I forgot to mention is an AC voltage source. So that would be something like this. What you plug, what you have on a wall. So you plug some kind of a wire in here like this, a plug. And these things are nominally supposed to be at 120 volts. So an AC source, unlike a battery where one end is always positive and the other one is always negative, for an AC source, AC stands for alternating current. Okay. So the direction of this current is always changing. So sometimes one side is positive, and another instant another side is positive. It's always switching back and forth. Hence the name alternating. The polarity is always changing. So these are typically what you encounter in household supply. They're at rather high voltages, and therefore it's kind of dangerous to touch any of these if you don't know what you're doing. So this is at 120 volts, and since I've been playing with electrical things since I was 8 or 10 years old, I've suffered shocks of 120 volts, 240 volts, and one time also 440 volts. I've been in the emergency room for electric shock, actually. So, lacks parental supervision. But so be careful about touching this. Don't repeat what I did. Don't end up in the ER. Once you get past things like these benign batteries, which are 6 volts, 10 volts, 3 volts and stuff like that, once you get into the 100 volts and higher than that, there is a risk of, you can get killed, actually.